The last functions that we will learn to take derivatives of will be the exponential and logarithmic functions. We've already talked about e to the x and natural log of the x, but we're going to extend this to all the exponential functions and all the logarithmic functions. And here we have a theorem that says that any a to the x has a derivative of natural log of a to the x. And that's very easy to show. If I take a function a to the x, pick whatever a you want, bigger than 0 and not 1, so 2 to the x, 1/2 to the x, whatever you want, and rewrite it as e of natural log a to the x, because the e and the natural log cancel out. That's a true statement. And then I'll use properties of logarithms to allow me to write this as e to the x natural log of a. This the x comes out in front on this exponent. And so writing it like that, trying to make it look like an e, but anyway. So now I can take the derivative of this because this is an exponential function. And so the derivative, we know by the chain rule, we take the derivative of e, which is e to the blank. We put the inside function back in, which is x natural log of a, and then we multiply by the derivative of the inside function. Well, that's the derivative with respect to x of x times natural log of a. But natural log of a is a number. A is going to be a given base for that exponential function, so it's 2 or 1/2 or whatever. And so what I'm taking derivative of is x times a constant. So like 2x, 3x, whatever. So all I get is that constant. So I get natural log of a from that derivative, e to the x natural log of a. That's the derivative, but I'm going to take this x back up into the exponent. I took it down up here, but now I'm going to take it back up into the exponent, and I get natural log of a, e to the natural log of a to the x. But e to the natural log gives me natural log of a, e, I'm sorry, the e's gone now, just a to the x, so canceling those out, which is what it says here. So it's easy to derive from what we already know, but if that adds all the other exponentials into our function that we can differentiate. And you can see the derivative of an exponential function is the exponential function, just like e to the x is. Derivative e to the x is e to the x. Derivative 2 to the x is 2 to the x. You do have to remember this constant that shows up in front. With e to the x, you get natural log of e to the x, so that constant doesn't show up because natural log of e is 1. So let's apply that. Looking, for example, here, you see a pi to the x over 3 to the x, and you might think use a quotient rule, which you can, but it's probably quicker to just do a little bit of algebra first, which is take that exponent out of each one of those and write that whole fraction as raised to the x power. That's still an exponential function. It's pi over 3 to the x. And so I can use this formula. Remember, the derivative of any exponential function is that exponential function, pi over 3 to the x. You just have to remember out in front of it is, and I didn't leave myself enough room, but out in front, there's going to be a natural log of the base of your exponential function. So it's natural log of pi over 3. And that's what you'd get if you'd use a quotient rule and simplify everything properly. But so exponential functions are nice. They're their own derivative with a little bit of a constant, unless it's e to the x, then it's just their own derivative. Well, then that allows me to expand this to a chain rule. If I want to take the derivative of a to the g, so base 2, base whatever, that derivative, I start on the outside. A to the x is the exponential function, is the outside function. And the derivative of a to the x is natural log of a to the blank. But the chain rule then says put the inside function back in and multiply by the derivative of that inside function. And so that's what we've got here. The g prime has just been moved more to the front. So in particular, e to the f is just going to be f prime e to the f, because you get natural log of e f prime e to the f. So that's an easy one to remember. You want to take the derivative of e to the f, it's f prime e to the f. Let's apply that to a couple problems. Here I've got 1/2 to the tangent x. So that's a composition of functions where it's a base 1/2 exponential function raised to the tangent x. So if I want to take the derivative, I know that that derivative is going to be natural log of 1/2 times the derivative of tangent times 1/2 to the tangent. So if you want to go through the actual chain rule, it's the derivative of 1/2 to the tangent. Well, that's natural log of 1/2, 1/2 to the blank, put the inside function back in, then multiply by the derivative of tangent. So it's just in a different order. So you can always go back to the actual chain rule to work it out, or you can have it memorized. It's basically f prime 1/2 to the f prime, but you got to remember the natural log of a half. But anyway, to finish this up, natural log of a half, derivative of tangent is secant squared. So there's my derivative. You could, if you wanted, you could break this 1/2. This could be written as natural log of 1 minus natural log of 2, which is 0 minus natural log of 2. So you could just rewrite this first part here as minus natural log of 2 times the rest of this stuff. But essentially the derivative, the part of taking derivatives was done in this first step. Just recognizing that a chain rule applied. And then the same way with the e. If you've got it memorized, when I've got e to the f, it's the derivative of that inside function times e to the f, e raised to that inside function. That's the chain rule. It's the derivative of e. This is my inside function. Then you have to tack on the derivative of that inside function. Well, now I've got a product rule. It's the derivative of x, which is 1, times tangent inverse, times, the derivative of tangent inverse, which is 1 over 1 plus x squared, times x. And then that's times e to the x tangent inverse x. Now there's not much I can do in here. If you want to find a common denominator, you can. It's not going to gain anything, but typically we do find a common denominator. It's going to be 1 plus x squared, so I'm going to end up with 1 plus x squared in the denominator. So this term, the second term, has already got that. This first term is going to have to be multiplied by 1 plus x squared, and then I've got my tangent inverse in there as well. Not leaving enough room for these anyway. And then all of that is times e to the x tangent inverse x. So just add some more functions to our list of functions that we can take derivatives of, all the exponentials, and then if you want to memorize the special chain rules for them, this one's the easiest to remember. Derivative of e to the f is f prime e to the f. Derivative of a to f or g or whatever is going to be natural log of a to the f times f prime. And then this one, like I said, moved it around. So we'll use these functions to help us figure out how to take derivatives of all the different logarithmic functions.